Swayam Prabha. Digital India. Educated India.
Welcome again. In the last two lectures, almost like a continuous lecture, we talked about the gross structure of brain and some microstructure and how it actually functions. So, and I hope you've got the idea of how actually the brain is creating behavior. But how did we come to know of all this? One thing which we discussed was like in the lesioned patient. People who had brain damage and the alteration of behavior was one way of looking at it. But as I said, that in the last 40 years we have known more about brain and really tried to peep into the brain. So, today we will try to look at in this talk we will try to look at how actually we try to understand what brain is doing. Now, ultimate aim and ultimate desire of every neuroscientist is to look into a live brain when it is functioning, but that is not possible because of clear cut ethical reasons. So, what are the tools to peep into brain? What is the universal tool to know the mind? Obviously, it is nobody better than you yourself, and half the time we cannot observe our behavior because, as I said, lot of it is unconscious behavior which is propelling you to do certain things, but whatever we know consciously we know. So, we try to look at the behavior of others, right, and what has helped us in looking at the behavior of others is a set of neurons which are more or less, we have not been able to spot them clearly in the brain, but we still know that there is a functioning of mirror neurons. Now, mirror neurons are active all the time, probably they have helped us grow as human beings, because one quality of Homo sapiens is that we were able to grow together. Unlike other animals, there are other animals who grow in herd, but and I am sure they understand and feel each other's emotion, but the way human beings have this capability of looking at the emotions of others and anticipating and predicting the future behavior, that is very, very unique, and mirror neurons have helped them a lot. These are the neurons which make you feel sad when you look at somebody's sad face. You can recognize anger by looking at the face of the other. You can even anticipate when somebody is getting angry, because if it is just visual input and the brain does not make interpretation that okay, this facial distortion corresponds to anger, then your mind will not even register, and that is actually one, that is the big problem in one of the illnesses which kids have called autism. Their recognition of facial emotion is hugely impaired, and that is what makes them socially, I mean the restriction in their social behavior is partly arising from them. So, animal and human studies is one of the ways to study. We study animal behavior because the brain structure is similar in lot of animals. Even the mouse has the same encephalization and the same type of network. And so, while human and monkeys are very different, some like macaque are extensively studied because of the similarity in the brain. That is one way of doing it, and as I said, the neurons that shape the world. So, if you look at the scale in which we study the nervous system, here is the size, here is the time. What are the ways? Lesion, it is a longer space time, 1 year, months, animals weeks to years, and the scale is very high, it is in centimeter to meter. Drug manipulation again from days to hours, EEG in minutes, an hour, PET scan, functional MRI, scalp PRPs. Patch clamp recording is when you really go to the neuron membrane and catch one of those transmitters or the receptors, micrometer. So, this is just to give a broad idea, this is the range within which we can study, and within brain what we are studying, synapse here, and when we are studying the human behavior, with the lesion, the patients or animal, it is the brain. Again the same thing, milliseconds to seconds to minute to hour to day, lesions, PET scan, fMRI, TMS. So, all these techniques, they are direct brain signals which are electromagnetic. They include EEG, MEG and single cell electrical recording. We can pump in some electromagnetic energy to stimulate neurons in the brain. The indirect signals are produced by the brain metabolism and blood flow. The brain utilizes about 20% of the energy of the body to keep it functioning and to keep it warm, glucose and oxygen with functional MRI and MRI, and radioactive tracers like PET, positron emission tomography. But they all have their pros and cons, and as you can fit this into this study of the scales. Now, if you look at the gross thing like lesions, so as I said, Fenner's gauge, if you remember from the previous lecture, the brain injuries can provide evidence that certain areas are necessary for certain functions. But when you study these brain areas damage and the subsequent behavioral changes, imagine now somebody has an injury in hippocampus and has a problem with memory. What you can best do is correlate it. You can say that okay, this area, damage to this area can lead to this deficit or this derangement of function, but whether it is causing that exactly is not certain. Like in stroke, in Broca's aphasia, there is a problem in creating language, in speaking, but that we do not know whether that is the end product, there is an end point in a series of functions of language creation, or they are, or it is the cause. That is certainly difficult to study in the brain lesion thing. The other common, the most popular investigation in brain has been CT scan, which is a attenuated X-ray, but CT scan just gives you a broad idea of any existing damage in the brain. Like in this case, there is something called hydrocephalus, where there is more fluid in the ventricles. Again, CT scan gives you a broad idea if there is a tumor, or if there is something called neurocysticercosis, or there is a stroke, there is a damage to the area because of the derangement in blood flow. CT scan is a good thing to take, but nothing beyond that. But it is one of the most commonest used investigation, especially in clinical settings, to rule out immediate damage to brain when we see neurological signs. In psychiatry, we do CT scan as a protocol, or when we are suspecting some organic, but CT has been surpassed by other investigations. One of them is like positron emission tomography, which was developed before functional MRI and provides a measure of metabolic activity, the activity of the brain. It is very expensive to use, is invasive, that there is a certain amount of radioactive dye which has to be inserted, and but lot of important work, as it says, has been done. It is slow, so fast activity in the brain cannot be caught, but what you can do is, if you give a certain task to the brain, or if you are suppose in clinical setting you are suspecting some tumor, there if you give a radioactive tracer and the activity increases in that area, like the deoxyglucose is more glucose consumption in those areas, that almost lightens up, it gives you an idea. But like here, you can see the hearing word, this area gets lightened up. Here seeing words, thinking about words, speaking words. Now this is the, when after infusing the radioactive tracer, repeated slices of brain tissue were taken on imaging and the image was captured, but these tasks had to be given for that person to do. Only then that area will take up, utilize more glucose and almost lighten up. Functional MRI is an improvement on MRI, which you all know, but just to reiterate. So this is the basics about MRI physics. There are protons in water, the hydrogens in H2O. They have a random magnetic spin. So the body part, the brain in this case, is put in the high magnetic field. So, they all protons line up with the same spin orientation. They all line up according to the, it's like here, it's the baseline. So, they line up according to the magnetic field, right. After that, there is another pulse, a radio frequency is sent, which actually shifts them from that aligned magnetic field. So, that is called precession, and then it again relaxes back to the original alignment. But these signals are caught. These are electromagnetic signals which are caught and with the surrounding detectors, and that constructs the image. They both rely on the subtraction method. So, the thing is that maybe if you put the detectors around the slice of the brain, obviously a live brain, and we put a magnetic field, the protons will orient, but it may be different from adjoining areas, because their alignment may be different. So, the image is formed in comparison to the, so it is like subtracted from the adjoining areas. Both PET and MRI work on subtraction method. So, you can see it here, it's stimulation activity minus control activity, it's equal to difference activity. So, what you are seeing is one slice of the brain for which the magnetic field has been, the detectors are covering that field, the magnetic field has realigned the protons in that slice, and you send a radio frequency. In the process of precession and relaxation, the signals are caught in that slice, and then you move on another slice, but this slice may have difference from the rest of it. So, that is the subtraction method. So, that is MRI, which is again used clinically. It is like more of a static investigation, you keep seeing slice after slice, does not tell you the metabolic activity, it tells you the structure like CT scan. PET whereas tells you the function. Functional MRI is an improvement which uses something called BOLT, blood oxygen level dependent activity. It is on the premise that if there is a certain activity in certain area of the brain, it will use more oxygen. So, normally if you put the person and the brain is at rest, brain is never at rest in one, but if you compare it with the activity level, it can still be at rest. There is a deoxygenated hemoglobin, the oxygen level is less, and there is a certain activity and it shows us a certain image. But if you give a task, so you should know what task are you giving and what are you suspecting and what are you expecting which area will get activated. So, you give a task according to the possible function of that area where you want to look at, which is called region of interest, and then as the oxygen level increases, the signal changes, because it will utilize more oxygen. So, it will for a moment it will go down, and then as the blood flow will increase there. So, as the blood flow will increase, the oxygen level will go up, that will create a difference between the resting state and the active state. So, this is the most popular neuroimaging technique used in research. And so, region of interest, as I told you, is a dynamic complex entity. How do you know which areas correspond? One technique is to define before scanning to identify the area where you expect to see the change, like face and location matching here, face matching. So, recent wave of brain studies, lot of it on right from cognition to motor movement to understanding emotions. Functional MRI is the in thing, and lot of research is being planned around that, even to an extent of coupling it with EEG. Like for example, this study compared brain activation for conscious and unconscious events. Unconscious viewing of words activated visual areas, whereas the conscious viewing activated expanded region in the cortex. So, this is unconscious. So, you are not putting your brain into it and you really see this area activated, but the moment you put your brain to it and you want to look at it, that means you have put your attention span. So, the whole activity level increases to the whole cortex. ERP is event related potential. Now, event is trying to respond to the words, we will talk about it when we talk about EEG. And as I said, resting brain is not silent. So, from the baseline, the protocol subtract an experimental condition, frequently what is called a resting state. While activity may not be directly related to the task, there is no task being given to the brain, but brain in itself even at a resting state is just not resting. It is, we are constantly thinking, imagining, memorizing, feeling. So, the brain is firing electrochemically all the time to keep a semblance of order, to keep the sense of unity, to keep you oriented to time and space, to keep you feel alive, right. So, as you see it here, this is the background activity is going on in resting state, left and right. So, there is so much of activity. So, there is really, we can call it a default mode network, which is a resting state when you are not voluntarily intending to do any task. There is another way of imaging, something called transcranial magnetic stimulation. We put a coil and stimulate certain areas of cortex. Again, this is also needs to have a region of interest, because we should know where are we stimulating and attributing what function to that area. So, this is, as I said, is a contribution of a specific brain regions to complex. So, if we think that okay, this is the area where mathematics, the area where mathematical abilities are governed from, and you stimulate that and see the effect of it, effect of this disruption of natural electromagnetism of brain through a pulse of magnetic wave, and see the impact on it through a hypothesis, it confirms what you are thinking, okay, and but if it does not, then obviously there has to be some other area. The big question in imaging in the brain and peeping in the brain is when or where. What is important? You want to look at the area where it is happening, or you want to look at it when it is happening, because obviously when and where is the orientation of space and time. So, the imaging has to answer this question, like MRI, CT scan tell you the spatial, whereas the functional MRI also tells you the spatial in a more confirmed way, in a hypothesis driven way, where it tells you, okay, you give a function, we suspect that this area is x, area x is causing function y. So, you look at x, give a task which will evoke function y. In functional MRI, you have to give a task. If you do not give a task, and as I said, resting state you can see here, but if you give a task, you may see things like this. So, sometimes what becomes important is to look at when it is happening. That is the temporal thing. So, this question is still, new techniques are being evolved where functional MRI and EEG both are being used together to look into the when and where, but it has its own limitation and not all of them is clinically useful. Okay, this is again, so there are T1 and T2 weighted images. There is something which looks at the movement of water in the white matter. White matter, as if you remember from the initial lecture, the white matter are the axon bodies which are covered with myelins and which actually form the neuron. So, this is diffuse tensor imaging which looks at the water molecule movement. So, this is all, if you look at it, this is a diffuse tensor imaging through the movement of water molecules delineating almost the white matter within the brain. You can fit this image into the network images which I showed you initially. So, the big question is, which is important for psychiatry now as we go more deep into human behavior, whether brain recordings tell us how humans behave. They are all indirect measures, like as I said, MRI looks into the subtraction method. Each type of brain recording tells us part of the story. Like MRI, in functional MRI, they tell you the spatial orientation, diffuse tensor imaging. Now, this is another image of the whole, the way white matter comes down to form the spinal cord. If you look at this, this is vision, hearing and Wernicke's area. It will all fall from the previous images, executive and Broca's area. If you, so olfaction, right. So, this is a white myelinated. You saw the myelin sheet, which increases the speed of nerve impulse transmission. So, essentially if I sum up till now, is that we have learned about the brain by looking at the lesions, people who have had brain damage, correlating it with the functions which have been altered through animal studies, through technology in the last 40 years by CT scan and MRI, which give you a structural image of the brain, through post-mortem studies by dissecting the brain after somebody has died and looking at, maybe we have not been able to locate the lesion while person was alive, but post-mortem told us, okay, the behavioral changes which he had in the lifetime were partly because of this area. And as technology is advanced through functional MRI, where you give a task and look at the images subtracting from the background, PET, diffuse tensor imaging, which gives you a damage to the white matter. All these things are used clinically and in research. But so largely what we know about the brain is that brain with 10 to the power 11 neurons is organized into almost parallel processing modular structure, where there are functional networks like default mode network at resting, certain areas involved in that. There is a central executive network, there is a salience network, and through which all the cerebral cortex, the various cerebral areas of cerebral cortex and both the cerebral hemisphere through corpus callosum are united. Brain is electrically active all the time. Action potential is the basis of all electrical activity between neurons. Synapses, synaptic information transfer happens through neurotransmitters, which are multiple dopamine systems, adrenaline system, the serotonergic system, which have cell bodies where there is a maximum concentration of these cell bodies, and they have diffuse projection. These and they keep firing. The cell assemblies are the neurons that fire together. They may be located in different geography, but at the same time, when they are activated, they will create the same function again and again. Functions are divided in various cerebral hemisphere and they coordinate with each other. Largely unconsciously, the brain is taking stimulus, information, processing, integrating, comparing it with previous memories, maps, putting it in the relevant hierarchy of emotion, presenting it to the conscious mind within 200 to 500 millisecond, and the brain deciding on whether to act or not. What has to go into the memory is potentiated through the short term memory through firing in hippocampus and Pepez circuit, and long term potentiation by synaptic changes. So, all that is for the whole complicated behavior which we have created. Now, we were looking till this point that how do we peep into the space, into the area where we want to look at it. Now, we will switch to, I also said that when are things happening is also important to know. So, in the next talk and the last of this first week module, I will tell you how do we look at when, and that would probably cover up more or less broadly about how the brain behaves, and then also introduce you to almost a sister branch to psychiatry, that is psychology. That in the next. Thank you.